So there's one more gas law that we need to learn about, and that is the ideal gas law. Remember, with the first gas laws we learned about, we know that the volume of a gas changes when the temperature changes or the pressure changes. Because of this, we know it's handy to measure the volume of a gas at standard temperature and pressure, because temperature affects the volume and pressure affects the volume. So it's nice to have a standard temperature and pressure so you can compare gases with each other. And we know that 1 mole is 22.4 liters of gas if you are at standard temperature and pressure. But we're not always at standard temperature and pressure. Sometimes the temperature and pressure are different to those standard conditions of 1 atmosphere and 0 degrees Celsius or 273 Kelvin. So how do we do calculations if we're not under STP conditions? We're going to learn the ideal gas law to help us cope with a situation like this. But first, let's just refresh our memories. There are 4 important physical characteristics for gases: pressure, volume, number of moles, and temperature. These 4 variables are related to each other in an equation called the ideal gas law: pressure, volume, number of moles, and temperature. The ideal gas law is used for situations where the conditions are not standard temperature and pressure, when the number of moles or the mass of a gas are given. Now, some of you may have noticed that there's this R value in here, and R does not stand for pressure or volume or number of moles or temperature. So what is this R value? This R value is the universal gas constant. Its value depends on what units we are using for pressure in particular. Remember, there are different units for pressure. Millimeters of mercury, or which can also be called torr. We can use kilopascals, we can use atmospheres of pressure, and the numeric value of R differs depending on which units we're using for pressure. So there are 2 commonly used R values depending on what units you're using. R equals 8.3145 liters times kilopascals divided by moles in Kelvin. If pressure is in kilopascals, notice the how kilopascals appears in those units. On the other hand, the R value is 0.08206 if pressure is in atmospheres. And notice that the units for this R value, liters times atmosphere divided by moles and Kelvin, notice that those atmospheres appear in the units there as well. So you need to use different values of R depending on whether you're doing a calculation in kilopascals or atmospheres. I could give you a separate value for millimeters of mercury, but really it's almost easier to just do the conversion into kilopascals or atmospheres and then use the appropriate R value. So let's look at some situations where you would use the ideal gas law. What pressure, this is our unknown, is exerted by 4.50 moles of a gas, so this is our number of moles, in a 198 liter, this is our volume, container at a temperature of 8 degrees Celsius. This is our temperature, but it's not in in Kelvin, so I need to convert this. This will be 281 Kelvin. Now, so just to summarize in a kind of table, what we know, what we don't know. We know the pressure, we know the number of moles. I'm sorry, we don't know the pressure. That's what we're trying to solve for. We know the number of moles. We know the temperature is 281 Kelvin. We know the volume is 198 liters. And because we're asked to give the pressure in kilopascals, we should use the R value that corresponds to kilopascals. So we were not given the R value in the problem, but it's a constant, and so we should know it. We should have that memorized, 8.3145. This is a great example for using the ideal gas law. Notice, unlike the combined gas law problems we did before, where you would have two examples of the same type of unit, like two temperatures or two pressures, we don't have that here. We have one pressure, one volume, one temperature, and one calculation for moles. This is the other giveaway here that we need to use the ideal gas law, is that we're given or are asked for a mass or a number of moles. Okay, so let's do our work. Our ideal gas law equation is PV equals nRT. So I plug in my pressure, or I don't know my pressure, so I plug in the letter P instead. My volume is 198. My N value is 4.50 moles. My R value is 8.3145, and my temperature in Kelvin is 281. If I multiply those numbers together and then divide both sides of the equation by 198 liters, then you see that the only units I'm left with are kilopascals, and my numeric answer to 3 sig figs is 53.1. Let's do another example. Find the volume of 85 grams. Let's see, find the volume. This is the thing I don't know. Of 85 grams. Notice I'm given a mass. We'll have to think about what to do with that value. Of oxygen at 25 degrees Celsius. So converting that into Kelvin, my temperature is 298. And 1.03 atmospheres of pressure. That is my pressure. So making a list of what I know. I don't know the volume. I know that I have 85 grams, but that's not the same as the number of moles. I'm going to have to think about what to do with that. I know that my temperature is 298. I know that my pressure is 1.03. And I know that because my pressure is in atmospheres, that I need to use the R value that corresponds to atmospheres of pressure, 0.08206. So what do I do with those numbers with those grams? My first step is to convert grams to moles. How do I convert grams to moles? I use my molar mass in a conversion factor. 1 mole is the same as 32 grams when I'm talking about oxygen. And therefore, I have 2.7 moles of oxygen. And now I have all the information I need to solve the problem. So I've got my PV equals nRT. I plug in my pressure, 1.03 atmospheres. I don't know my volume, so I leave it as V. I plug in my number of moles, I plug in my R value, and I plug in my temperature. Solving for V by dividing both sides of the equation by 1.03, dividing by 1.03, I get as my answer 64 liters. Let's look at another example. How many moles of oxygen, how many moles, so I'm trying to calculate N, the number of moles, occupy 15 liters, that's a volume, at 97.3 kilopascals, that's a pressure, and 21 degrees Celsius, that's my temperature, and that corresponds to 294 Kelvin. So to put that in table form, it's the number of moles that I don't know, but I know my pressure, my volume, my temperature, and the R value is the R value that corresponds to my pressure in kilopascals. So I choose the 8.3145 value for R. And then I plug my numbers into the ideal gas law equation, PV equals nRT. I know a pressure, I know my volume, I don't know the number of moles, so I use the letter N to represent that. I plug in my R value and I plug in my temperature. In this example, it might be easier to combine numbers together here. So 97.3 times 15 gives a value of 1,495.5. Multiplying these two numbers together gives a value of 2,444.61-ish. So if I divide both sides by the 2,444, then you get as your final answer 0.597028, although we need to round to 3 sig figs because my weakest measurements here have 3 significant figures. So I get 0.597 moles of oxygen gas. Let's do another example. What volume does 1.26 moles of carbon dioxide occupy at 103 kilopascals and 25 degrees Celsius? Moles indicates a measurement of number of moles. And we want to calculate the volume. This is the thing that we don't know. Kilopascals, remember those are units for pressure, so this must be a pressure here. And then my temperature, if it's 25 degrees Celsius, you add 273 and you get 298 Kelvin as your value for temperature. So to make a list of what we know and what we don't know, we know that the pressure is 103 kilopascals, and because of those units for pressure, then we need to choose the R value that corresponds to kilopascals. We don't know the volume. We do know the number of moles, and we do know the temperature in Kelvin. So when we have our PV equals nRT equation, and we plug in our values, we use 103 for pressure, we don't know our volume, 1.26 for number of moles, our R value, and 298 Kelvin. Doing the math here, here you get a value of 3,122.1162, something like that. You divide away the 103 from both sides of the equation, and you're left with a value of V equals 30.3 liters when you go to 3 significant figures. One final example. What is the temperature of helium if 12.5 grams, so we're given a mass here, not a number of moles, we'll have to remember that, occupies 65 liters, that's a volume, at a pressure of 1.10 atm, so that's our pressure. And we want to know what is the temperature. So if I'm doing PV equals nRT, my pressure is 1.10 atm, my volume is 65 liters, my N, I don't quite know what number to put there yet. I'll come back and revisit that. But because my pressure is in atmospheres, then I know that I must use my R value of 0.08206. And the units for that are atm, liters over Kelvin, and moles. And my temperature has a is what I'm trying to solve for. So I'll leave that as the letter T. Now here I need to put a value for my number of moles, but I'm told that I have 12.6 grams of helium. 12.5 grams of helium. So if I've got 12.5 grams of helium, and I want to know how many moles of helium that is, then I need to look on the periodic table and see that I have a value of 4.00 grams of helium for every 1 mole of helium that I have. Doing the 12.5 times 1 divided by 4 gives you an answer of 3.125 moles. Now this is actually only accurate to 3 sig figs, but I'm going to leave it as it is for right now because when I put this number into my next problem, this volume in liters here only has 2 sig figs, and I'm going to have to round my final answer to 2 sig figs anyway. So I'll wait till the very end to do my rounding, just to avoid some rounding errors. So if I do my 1.10 times 65, I get an answer of 71.5 ATM times liters. And on this side of the equation, if I multiply my two numbers together, number values together, I get 0.25644 if you round it off. And my units there, my moles, cancel out with moles, and I'm left with atmospheres, liters per Kelvin. Of course, I still have my temperature value here, and I want to get rid of this number so that I have the temperature all by itself. Because the temperature is being multiplied by that number, I have to do the opposite. I have to divide it away. 0.25644. Do the same thing to both sides of the equation so that the sides stay equal. Notice that my atmospheres and liters cancel out with my atmospheres and liters, and then I do 71.5 divided by 0.25644, and I get an answer of, according to my calculator, 278.82 Kelvin. Those values canceled out. So this is my value for temperature. Remember I said before that because of this multiplication problem, and this is the weakest measurement with only 2 sig figs in my problem, I'm going to round my final answer to 2 sig figs. Remember, in a situation like this, don't round it off to 28. The final answer is 280. We need that 0. It's not significant, but it's an important placeholder to keep the 2 in the hundreds place. So our final answer here is 280 Kelvin. I hope this helped.